For the Bohr hydrogen atom, we're going to determine the energy of an electronic transition, its frequency, its wavelength, and whether that transition falls within the visible region of the electromagnetic spectrum. So in our particular problem that we're going to look at, we have electrons in the hydrogen atom, and the transition is going to be from the N4 down to the N3 level. We're going to calculate the energy, the change in energy of that transition, or the energy related to that transition, its frequency, its wavelength, and whether that transition falls within the visible region. All right, let's remind ourselves how we view the energy levels. Down here we have the nucleus, and then as a two-dimensional cutaway, we have our energy levels N1, N2, N3, N4, and then theoretically on up to infinity. In our particular problem, we're to identify the energy related to the transition of an electron in the fourth energy level, transitioning down to the third energy level. The way that we're going to identify this is we're going to calculate the energy, in which the energy of the transition, delta E, equals minus 2.178 times 10 to the minus 18 joules, multiplied by the inverse of n f squared minus n I squared. In our case, we're looking at an electron that's in the fourth energy level going down to the third energy level. And we're identifying here is that in that transition, the initial n level is the fourth energy level, and the final energy level is the third energy level. So our transition, the electron is transitioning from a higher energy level down to a lower energy level. So let's go ahead and do that calculation, in which we have delta E equals minus 2.178 times 10 to the 18 joules. 1 over our final is 3 squared minus the inverse of 4 squared. The change in energy, or that energy gap, equals a minus 2.178 times 10 to the minus 18 joules, multiplied by the inverse values of 0.1111 minus a 0.0625. Delta E, the energy related to that transition, equals a minus 1.056 times 10 to the minus 19 joules. All right, and when it comes to energy, we've calculated a negative energy value, and what that negative energy value depicts is the direction that the electron is transitioning from. A negative value implies that the electron is falling from a higher energy level down to a lower energy level. That the connotation to the negative implies that the atom is becoming more relaxed, it's releasing energy, and that carries a negative notation. The change in energy being positive would imply that the electron is going from a lower energy level to a higher energy level. So the sign of the value of the energy is just designating the direction the electron is flowing. From a negative implies from a higher energy level to a lower energy level. The system is giving off that amount of energy, it's relaxing. A positive energy value implies that the electron is going from a lower energy level to a higher energy level and is absorbing that energy. So when it comes to the value of the energy gap, the negative positive just designating the direction of the electron, but the overall energy level is, in our case, the 1.056 times 10 to the minus 19 joules. So that allowed us to calculate what we had just finished calculating is the energy related to the first part A. What we are now going to calculate is the frequency associated to that energy transition. When it comes to frequency or wavelength, they are all positive values. We don't have negative frequencies and we don't have negative wavelengths. So when it comes to calculating the frequency, what we have here is we're going to have the energy equals a Planck's constant multiplied by the frequency. And what we just calculated is that energy transition. And so if negative, we will drop that negative value and then go ahead and calculate the related frequency. The frequency equals the energy divided by Planck's constant. So H is Planck's constant, and Planck's constant equals 6.626 times 10 to the minus 34 joules dot second. All right, in calculation, frequency equals the energy that we just identified, being the absolute value of it, which is the 1.056 times 10 to the minus 19 joules, divided by Planck's constant, 6.626, times 10 to the minus 34 joules dot second. The frequency, and we also want to note what units that will be in. The frequency equals a 1.599 times 10 to the 14 reciprocal seconds, times 10 to the 14 reciprocal seconds. All right. We have our frequency, and again, just on the units, we do want to track the joules canceled out, and we are in reciprocal seconds for frequency. All right, so with that then, we have calculated the frequency. And now what we want to calculate is the wavelength associated to that frequency. All right, so what we have here is we have frequency. We have frequency multiplied by wavelength equals the speed of light. And the speed of light equals, we're going to use the value of 3.00 times 10 to the 8 meters per second. Okay? And we want to identify our units using that particular constant for the speed of light. So we have the wavelength equals the speed of light divided by the frequency, which we just calculated. Therefore, the wavelength equals 3.000 times 10 to the 8 meters per second divided by the frequency, and that frequency was 1.5993 times 10 to the 14 reciprocal seconds. Okay? So in that, we go ahead, again, we would like to track our units in which the reciprocal seconds are canceling out, and that wavelength, it will be in meters, and that wavelength equals, 1.875 times 10 to the minus 6 meters. And that's the wavelength. We were asked in the problem, we were asked to identify this wavelength in nanometers, because many of us have committed to memory what the visible region of the electromagnetic spectra is in relative nanometers. So we have it in meters, and let's go ahead and convert that into nanometers. So what we know is we know 1 nanometer equals 1 times 10 to the minus 9 meters. The wavelength equals 1.875 times 10 to the minus 6 meters multiplied by 1 nanometer divided by unit conversion 10 to the minus 9 meters. Let's go ahead and identify now in nanometers what the value of the wavelength is. So the wavelength equals 1,875 nanometers. And that is the wavelength in nanometers, 1,875 nanometers. So what we identified here in nanometers is the wavelength, and that would be right here. Then we are asked, does this fall within the visible region? And when we look at the electromagnetic spectrum, this is the electromagnetic spectra from gamma radiation down to radio frequency. The top part is identifying the spectrum in terms of meters, wavelength. And as we see, as the wavelengths increase, the energy decreases. Or one could think about it in terms of frequency, which is the bottom scale. But we're focusing on the wavelength in terms of nanometers. And for the visible region, it falls, a wavelength that would appear in the visible region falls between the region of 400 nanometers up to 700 nanometers. And the question is, will the transition that we just determined from electron going from the fourth energy level down to the third energy level, does it fall within this region? And so we identified our wavelength equaling the 1,875 nanometers. So it does not fall within the visible region, meaning we will not see that transition as a color. Our eyes will not detect it as a color of light. It will not appear in the line emission spectra associated to hydrogen. Is it occurring? Yes, but will we see it? No. And then we could ask ourselves, based on the wavelength that go to the top, we identify it in terms of meters. We had determined the top scale is in meters. We determined that that wavelength is 1.875 times 10 to the minus 6 meters. So where does it fall in the electromagnetic spectrum? It's larger than what occurs in the visible region, and so that transition would fall in the infrared region times 10 to the minus 6. And that is the determination of electron transition for the Bohr hydrogen atom.